All right, expressing in polar form. So let's just draw this guy up here for a minute. Here's our Argand diagram, our complex plane. There's the real part of Z, the imaginary part of Z. Say that's root 3 there and that's 1. Then that point there is the point 1 root 3, representing 1 plus root 3i. So that's what they're wanting. That's our argument in there, our argument of that, and so we can use this triangle, which has root 3 on there and 1 there, to work out what we need. So from there, tan of theta is equal to root 3 on 1. So tan theta is root 3. So theta is pi on 3. Now that falls into the correct range between minus pi on and pi. So that's a good argument there. And we use Pythagoras' theorem to work out the modulus. So let's work out the size of the vector out to 0.1 root 3 by doing Pythagoras. And we got root 3 squared plus 1 squared. So 3 plus 1 is 4. So root 4 equals 2. All right. So this is 2 cis of pi on 3. Or if you like, 2 times cos pi on 3 plus I sine pi on 3, polar form. So it has a modulus and an argument. Next one, we've got to solve this quadratic, which has, it's got complex coefficients, and we've got to give the answer in exact Cartesian form, which is like a plus bi. Okay, so, or x plus yi. So I'm going to use quadratic formula. I could complete the square there. I'm going to use the quadratic formula. So we've got that z equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So minus 2 plus or minus root of 4 plus 4 root 3i on 2. That 4 under the square root sign can be factorised and brought out of the square root sign to become a 2. Root 3i on 2. Just scroll down, get a bit of room there. And we factorise out that 2, minus 1 plus or minus root of 1 plus root 3i. Now we need to express that in the form a plus bi. So we go back up and look at what we had in the question 1. 1 plus root 3i can be expressed as 2 cis pi on 3. So the stuff under the square root sign here, 1 plus root 3i, is 2 cis pi on 3. All right, I'm just going to go up here and work out what is the square root of 2 cis pi on 3. So like I'll arrow that so anyone looking at my work can see that's what I'm doing. That's the same as 2 times cos pi on 3 plus I sine pi on 3, and all of that is raised to the power of a half. So it's 2 to the half and cos pi on 3 plus I sine pi on 3 to the half. So that's root 2. And then by De Moivre's theorem, we multiply each of these arguments by half. So it's cos n times pi on 3, a half times pi on 3. So pi on 6 plus I sine a half times pi on 3, which is pi on 6. So this is root 2. Cos pi on 6 is root 3 on 2. And sine pi on 6 is a half. So that's root 6 plus root 2i on 2. All right, so that can get pumped back into here. We've got minus 1 plus or minus root 6 plus root 2i on 2. So let's put it all on 2. Minus 2 plus or minus root 6 plus root 2i in brackets all over 2. I do need to be careful because this vinculum, this here vinculum, fraction bar, acts as, or it is, a form of grouping symbol. So always it's as if it's bracketing its top line and bottom line. All right, so I'm just going to separate these out into their two solutions now. We've got minus 2 plus root 6 plus root 2i on 2, or minus 2. Now, I've got to be very careful because when I do this bit, this minus sign that I'm going to distribute, it's got to distribute across this. So I'm actually going to end up with minus 2 and then minus root 6 minus root 2i all over 2. I think I could tidy that up just a tad, write it out more neatly. So doing that again, I get minus 2 minus root 6 and minus root 2i. So if I get all the whole number bits together, I get minus, well, not whole, real numbers together, I get root 2 plus root 6 on 2 plus root 2 on 2i with the complex bit. And over here, I get minus 2 minus root 6 on 2 and minus root 2 on 2i. So that's given then in Cartesian form.